All right, so in this section, we're going to look at what are called vectors, and we're going to be doing a lot of calculus with vectors later in the semester. So we want to start by introducing ourselves to this concept. So let's get started. What is a vector? And you might have seen these in pre-calc. You probably definitely at least were introduced to the idea of a vector in terms of graphing them, doing algebraic manipulations with them. But a vector is a quantity that has both magnitude, meaning length, but it also has direction. Some examples you may have seen in physics: force is a vector, velocity is a vector, and displacement is a vector. So things like speed and distance would be what are called scalars. They only depend on length or size. They don't depend on direction. Whereas velocity, if I say I'm going negative 50 miles an hour, it indicates that I'm moving 50 miles per hour, either maybe to the south or to the west. It gives me an indication of the direction that I'm traveling. Notations for a vector. Typically, a vector would look like this. It has a starting point, and it moves towards a specific ending point, and we draw an arrow to indicate the direction of motion. So this vector here, you'll notice, has a little bold-faced V. That's one way you can denote the vector. On paper, when you're drawing these by hand, typically what you'll do is you'll put a little arrow above the lowercase letter, or you can do a half arrow. So I could denote it like that, or I could draw it like that. Hard to do the bold-faced drawing by hand. So textbooks will often do this, but when you're writing your vectors on like a quiz or a test or on your homework, you'll want to put either a little half arrow or a full arrow above your vector. You could also, if they're listed with points, you could list the starting point first and then the ending point second. So the vector that starts at A and ends at B would be vector AB. Whereas if I started at B and I ended at A, that would be vector BA. So the order matters if you're going to use the points to list it. Okay. So in our vector above, A is where we start. So that's called the initial point. And so that's the tail. And B is the terminal point. That's where the vector ends. So we call that the tip. That's where the little arrow is. And that's where the vector's heading towards. Another idea to talk about is what are called equivalent vectors. These are vectors that have the same length and the same direction, even though they might be in different positions. So these two vectors that I have here, both of them are moving in the same general direction, and they both have the same length. So I would say that V and U are equivalent vectors, and I could say that U is equal to V. Now, this is a very basic sketch. We'll find, we would actually have to calculate their lengths and calculate their directions to actually confirm this, but this is just giving us the definition. Okay. So same length is one characteristic, same direction is the other characteristic. The zero vector is the only vector that actually has no direction. It has zero length, and because there's no length, I can't even see it. It has no direction, but every other vector will have a direction. Okay, vector addition, we're going to start graphically, and then we'll move into the algebraic side of vectors. If I want to add two vectors, the strategy we're going to use is what's called tip to tail. So basically what that means is if I want to add two vectors together, I'm going to look at the tip of where one vector ends, and I'm going to attach the tail of the next vector, and then I'm going to draw my resulting vector. So I'll show you what I mean by that. Let's say I wanted to draw A plus B. So A points directly up like this. I'll do a different color. B's pointing southwest like this. If I wanted to draw A plus B, I'm going to draw A. Actually, I'm going to move it over a little bit so I have room. I'm going to draw A. There's A. Do it in red. At the tip of A, so where the little arrow is, I'm going to attach B. Because I remember, vectors I can pick up and move wherever I want. Okay, so there's B. And then I'm going to draw the final resulting vector. A plus B is going to be the vector that starts at the very beginning where I started and ends at the very end of where I finished out at B. So it started at the bottom of A. It finished where the green arrow is for B. So my resulting vector, A plus B would be that blue vector right there. Now, is it commutative? Is really the natural question, meaning does A plus B equal B plus A? Well, let's graph them in the opposite order. Let's say I did B first. So there's B. Now I want to attach A onto the end of it. Move this over here. There's B. Now I want to draw A. There's A. And so then again, tip to tail, there would be my resulting vector. Different position, but both of the vectors look the same in the end. This would be A plus B, and it's the same as B plus A. So it does give me the same vector. And yes, A plus B is equal to B plus A, as we would expect. We also have what's called scalar multiplication. So we can multiply a vector by different numbers. If C is a scalar, that just means a number, not a vector. And V is a vector, C times the vector V is the vector whose length is given by the absolute value of C times the length of V, and whose direction is the same as V if C is positive, and opposite direction of V if C is negative. All that means is that if there's a negative number in front of the vector, it's going to multiply it by the size of the positive number, but it's going to switch directions because of the negative sign. So for example, if this vector here was V, 2 times V would just be a vector that has the same direction, but it is twice the length. And you can see that there's 1V, and then if I attach another one, there's 2V. But what if I did negative 2V? Negative 2V would be the same length, but it would be moving this way instead. So the negative sign switches the direction. The absolute value of the number in front tells you the size. And you can make them smaller too. 1/2 V would take the vector V and it would cut the length in half, but it would keep the direction the same. So just some different examples. So that kind of gives me a way to be able to graph subtraction. If I wanted to graph A minus B, well, I'm just going to think of that as adding negative B. So I'm going to go to A. There's A. Here's B. So I'm going to think about what negative B would be. LOL. So it's going to have the opposite direction as B, but the same length. So you can I'm just judging the size based on my fingers. So I'm going to move that vector. Here's A. And then here's B, or negative B, sorry. And so I'm just doing A plus negative B. And so my final resulting vector would be, there's A minus B, or A plus negative B. So having this idea of scalar multiplication allows us to subtract vectors and graph them. And we can combine all this together. What if I wanted to do A minus 2B? Well, I'm going to think of that as A plus negative 2B. So I'm going to start with A. There's A. Maybe a little bit too long. Let's shorten that a little bit. There's A. All right, well, here's B. So let me think. Here would be roughly, that would be 2B, but I want negative 2B, so I'm going to want it to go this way. I'm going to do that in red. So I'm going to take this red vector, negative 2B, and I'm going to move it here. And then I'm going to go tip to tail. I'm going to graph the final one in green. So A plus 2B A plus negative 2B would be the green vector. Okay. We can graph vectors on the coordinate plane. It's very much like plotting an ordered pair, except we draw a directed line segment to that specific point. So if we were to place the initial point of the vector at the origin, which is common convention, and the terminal point of A has coordinates of the form A1, A2, if we're working in R2, or A1, A2, A3, if we're working in R3, the ordered pair would just be the black point that you see on the screen. This would be A1, A2 right here. And this point right here would be A1, A2, A3. So that's just an ordered pair. If I want to make it a vector, I need to draw the actual arrow out to that point, makes it a directed line segment. And now how do I distinguish the vector from the point? I use this bracket or component form. So instead of giving it parentheses, I put a little set of brackets around the ordered pair. And that tells me that I'm dealing with vector A as opposed to the ordered pair. Okay. So brackets versus parentheses is a way to distinguish an ordered pair from a vector. Okay. And you can always move a vector so that its initial point is at the origin. All of these vectors in pink here are equivalent to OP. If I look at OP, it goes 3 units to the right and it goes 2 units up. So in component form, it'd be 3, 2. 3 units right, 2 units up. But all of these vectors that I've moved, move 3 units right and 2 units up. So they all have the same magnitude and they all have the same direction. So they're all equivalent. Okay. If I want to create a vector between 2 ordered pairs, say I was starting at point A and ended at point B, and I wanted to say what vector describes that directed ray, all I would do is I would subtract x coordinates, subtract y coordinates, and subtract z coordinates. Terminal point minus initial point for the x coordinates, terminal point minus initial point for the y coordinates, terminal point minus initial point for the z coordinates. So it has to be ending point minus starting point when you're writing your vector. So find the vector represented by the directed line segment with initial point. So we are starting at 2, -3, 4. Terminal point, we are ending at -2, 1, 1. So all I'm going to do to make the vector, starts at A, ends at B. So make my vector notation. I'm just going to subtract starting or terminal point minus initial point. -2 minus 2, 1 minus -3, 1 minus 4. So I end up with -4, 4, -3. Give me 1 second. Okay. So that would be my vector. Okay, so now we get into some of the algebra of vectors, which is a little bit easier than graphing them. Arithmetic operations with vectors works very much like what you would expect. If you want to add 2 vectors together, you can add their components together. If you want to subtract 2 vectors together, you can subtract their components together. If you want to perform scalar multiplication on a vector, you can distribute the scalar to each component of the vector. So that's all these are saying here. We'll look at some examples on the next page. And the same would be true if you were working with a vector in R3. So this is for R2. If you added a third component into the vector, you would just have to do this one more time. Some other properties of vectors, you can read through these on the notes. I'll just point out a few. This is the commutative property that we talked about earlier. This is the associative property. This is the additive identity. If you add 0 to a vector, you still get the same vector. If you add the negative of a vector, you end up getting the 0 vector. This is what's called the additive inverse. These are distributive laws of vectors. You can distribute a scalar to 2 vectors. You could distribute a vector to 2 scalars. More associativity, so this would be another associative law. And then this is what's called the multiplicative identity. If you multiply a vector by 1, you still get the same vector. So again, these are, I would say, all properties that are probably pretty obvious, or that shouldn't surprise you. But really, I'm not gonna quiz you on these properties with just the vectors. I'm gonna make you do them with some algebra. So. Okay, we have to have this idea of what's called the magnitude or the length of the vector. And we mentioned that vectors depend on magnitude and direction. So how do we actually calculate the magnitude or the length of a vector? Also, you might hear this referred to sometimes as the vector's norm. Might be a phrase that I use. So the norm is just referring to the length or the magnitude of the vector. And really all it is, if I want to know how long a vector is, look at it in R2 for a minute. let's say I want to know how long this vector A is here. Well, if it's got an X component, I'm going to decompose it into its X and Y components here, tip to tail, right? If this is A1 and this is A2, and I want to know how long that vector is, the notation that we use, you might see a single set of bars surrounding the vector. I like to typically use a double set of bars, depends on what textbook you're using. Those both refer to the norm or the magnitude or the length of the vector. It's really just Pythagorean theorem. If I wanted to know how long this hypotenuse of my triangle was, I would do a squared plus b squared equals c squared. So I would end up with a1 squared plus a2 squared equals the length of that vector, a squared, and then I would take the square root. So all I'm really doing is Pythagorean theorem. I'm squaring the components and I'm adding the results together and taking the square root. If you do it in R3, you have to add on a third component as well, because you'd be working three-dimensionally. Some other vocab, a vector with a length of 1. We're going to be dealing with these a lot this year. This is what's called a unit vector. These are what we call standard basis vectors. In physics, they're used a lot. And these are just the vectors that define, really any vector can be represented in terms of these standard basis vectors, 1, 0, 0, 1. If you're working in R3, 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are really the vectors that create the coordinate axes, the x-axis, the y-axis, and the z-axis. Any linear combination you take of these vectors can create any other possible vector you've ever thought of. And so usually we give the letter I represents the vector that points in the direction of the x-axis. That could be 1, 0 or 1, 0, 0. The letter J, and they're vectors, right? So notice that they're bold-faced. So when I write them by hand, I'm going to write them like this. J is the vector, the unit vector that points in the direction of the y-axis. So 0, 1 if I'm working in R2, or 0, 1, 0 if I'm working in R3. And then K only exists in R3 because it points in the direction of the z-axis. So that would be the vector 0, 0, 1. So they are special unit vectors that point in the direction of the x, y, and z-axes. And so, as I said, any vector you can express in terms of the standard basis vectors. So if I wanted to express the vector 1, 3, negative 4, well, if I think about that, that's 1 times 1, 0, 0 plus 3 times 0, 1, 0 minus 4 times 0, 0, 1. Since this is the x coordinate, this is the y coordinate, and this is the z coordinate. But this first vector is just I, the second one is just j, and this third vector, 0, 0, 1, is just k. And so this vector could be represented as I plus 3j minus 4k. Component form, standard basis form, you'll see both in problems that we cover this year. I usually don't care what form we leave it in unless the directions specify. We're talking about the same vector. It's just a different way of writing it. Okay, so let's practice some of these computations. A lot of different things you can do. Here's my two vectors. I usually like to start in component form. It's easier for me to see. So I'm going to write this vector u as I minus 3j plus 2k. That's 1, negative 3, 2, if I write it in component form. And v is I plus j. Notice they only gave you two components, both of which have coefficients of 1. Since the first vector did have 3 components, we do want to put a 0 in the third spot here, since we have to make sure if we're going to add vectors, they have to have the same number of components. So for the first one, if I do u minus 4v, I'm taking 1, negative 3, 2, and subtracting 4 times the vector 1, 1, 0. So I get 1, negative 3, 2. I can distribute. So I end up with minus 4, 4, 0, and then I subtract component by component. So I get negative 3, negative 7, 2. I do the x components, I do the y components, and I do the z components separately. And you could write this, I'll do this for the first one. You could also write this with the standard basis vectors if you want. I'm not going to do this for each problem, but on WebAssign, just look at what they ask for. They usually will specify. Okay. Find the magnitude of u plus the magnitude of v. Now, notice in part C, we have something that looks a little bit different. So I'm going to read this again. Part B is the magnitude of u plus the magnitude of v. In part C, we have the magnitude of u plus v. So the question you might be wondering is, are they equal? I'm going to put question marks. I'm not saying they are. Let's compute them and see if they actually end up having the same length. The magnitude of u, I'm going to have to do square each component and then add the results together and take the square root. So if I look at u, I got 1 squared plus -3 squared plus 2 squared would be 9 plus 4 is 13 plus 1 is 14. So this would be square root of 14. Magnitude of v, now I'm over here, 1 squared plus 1 squared plus 0 squared would be square root of 2. And so magnitude of u plus magnitude of v would be square root of 14 plus square root of 2. Not much else I can do with that. Magnitude of u plus v, the way I have to read this one, I have to do the addition first, then take the magnitude at the end. That's important. For the first one here, I took u, then I took its magnitude. I took v, then I took its magnitude. The final thing I did is I added the results together. Now I'm actually going to do the addition first. So u plus v, if I add components, 1 plus 1 would be 2. -3 plus 1 would be -2. 2 plus 0 would be 2. And so I end up with, if I do magnitude of u plus v, square root of 2 squared plus -2 squared plus 2 squared. 4 plus 4 is 8 plus 4 is 12. So I get rad 12 or 2 rad 3. You check this on a calculator. These are not equal. Rad 14 plus rad 2 is not the same as rad 12. So what this goes to show, I'm going to put a note here, might be worth writing down. Now, there are certain cases that you might be able to find some vectors where that does hold true, especially if one of those vectors was the 0 vector, then it would be a true statement. The magnitude of u plus the magnitude of v in general is not equal to the magnitude of u plus v. So here's a counterexample to show that we just did. Any important point to make note of. Okay. Next up, we have, I'm going to actually write v again since we're going to need it here. V was, what was v? V was 110. Okay. So, next thing I want to do is I want to take the vector v and multiply it by 1 over its magnitude. A lot of times you'll see this written as v divided by the magnitude of v. Might seem like a strange computation, but we'll see in part E why this is actually useful. So we know v, the magnitude of v we did compute earlier. The magnitude of v was 1 squared plus 1 squared. Square root is rad 2. So I'm going to take 1 over rad 2 and multiply it by, so I'm doing this right now, v over magnitude v. 1 over rad 2 times the vector v, 1, 1, 0. So in other words, I'm taking every single component and dividing it by rad 2. 1 over rad 2, 1 over rad 2, 0 divided by rad 2 is 0. And don't worry, you don't have to rationalize your denominators in this class. You can leave them as is. Okay, so probably doesn't seem very interesting. Now, look at part E, though. Look at what we're doing. Now we're taking the magnitude of that vector that we just found in part D. So I'm going to be taking the magnitude of this vector 1 over rad 2, 1 over rad 2, 0. So if I take that magnitude, I'm going to get square root of 1 over rad 2 squared plus 1 over rad 2 squared plus 0 squared. 1 over rad 2 squared would be 1/4. No, it wouldn't. It would be 1/2, sorry. Plus 1/2 plus 0. So I get square root of 1/2 plus 1/2 is 1. So why is this interesting? Okay, maybe pause me for a minute and see if you notice anything about that vector. Okay, so what's interesting about it is it's a unit vector. What we did is we took a vector that originally didn't have a length of 1, and we found a way to give it a length of 1. How did we do that? We divided by its magnitude. And so what we've done here is we've created or found a way of making a unit vector. And as I said, I believe earlier, we're going to be doing a lot with unit vectors in this course because we don't want to over magnify or give too much magnitude to things like the derivatives that we're taking. So unit vectors will play a big role, especially in chapter 14. Okay, so the process of obtaining a unit vector with the same direction as v, and that's important as I didn't change the direction, right? Here was v. All I did is I scaled it down in size, and this would be v over magnitude v. The blue one would have a length of 1. The full one doesn't necessarily have to have a length of 1. But this process is what's called normalizing the vector. It's the process of creating a unit vector with the same direction as the original vector. And so that's a skill that you need to be able to do. Something I could ask you to do on a quiz or a test is find a unit vector in the same direction as a given vector. So this vector, A, is given as 1, -3, 2. I'm going to switch it to component form. Find the unit vector that has the same direction as A. Well, definitely not a unit vector. If I square those components and add them together, I'm not going to get 1. But I want to create a vector that still has the same direction, but has a length of 1. So what I'm going to need, this is my goal, is I'm going to need to take A and divide it by the magnitude of A. So first thing I need is the magnitude of A. So I'm going to take 1 squared plus -3 squared plus 2 squared. 9 plus 4 is 13 plus 1 is 14. So all I'm going to do is take each component and I'm going to divide it by rad 14. So A, and remember, make sure you're putting your arrows above your vectors. That's something that you got to make sure you're including. This would be 1 over rad 14, -3 over rad 14, 2 over rad 14. And you could also leave the 1 over rad 14 factored out on the outside if you want. This would also be an acceptable way of leaving it. You could also rationalize your denominators. Any equivalent exact form would work. And as an exercise for later, I'm not going to do the algebra right now, but take the magnitude of this vector. What you should see is that if you take the magnitude of this vector, the magnitude of this vector should be 1. So that's a good way to check your work. We can do some of these vector computations with trig, and that's going to be helpful when we get to some of the word problems that deal with force near the end of the section. So vectors determined by length and an angle. We can express any vector v in terms of its length and the angle theta made between the vector and the positive x-axis. So this should make you think of the unit circle. Okay? If I have a vector v and I want to express its components, well, if I look at this angle between the positive x-axis, I'm going to call this theta, and my vector, I can decompose this into a right triangle, and I can look at the components of that vector. There's one component in green, there's one component in red, and notice this green component, using a little bit of SOHCAHTOA, a little bit of trigonometry, this would be the magnitude of v times the cosine of theta, and the red direction, or the red component, would be the magnitude of v times the sine of theta. And so any vector v can be written as magnitude v cosine theta for the x component, magnitude v sine theta for the y component. And notice both of those components have a magnitude v involved, so we can factor that out. And so any vector can be written as its magnitude times the cosine of the angle between the vector and the positive x-axis, and then for the y component, the sine of the angle between the vector and the positive x-axis. So they could give you the angle, that would be pretty straightforward, or they could give you the vector. So let's do that, work backwards. Let's find the angle that the vector -rad 3, 1 makes with the positive x-axis. It helps me to sketch it out and look at it. This would be in quadrant 2. -rad 3 is a little bit more negative than -1. So if I'm graphing this vector, it's going to land me somewhere about there. Okay, so that would be my vector. And so if I look at it, I can definitely start by writing out what I know. I know the magnitude of the vector is going to be negative rad 3 squared would be 3 plus 1 squared would be 1. So this would be rad 4. So I know the length of the vector is 2. Okay. So I'm going to set up my little structure of my formula up here. And you could do this purely with the geometry. If you made a triangle here, you could probably do the entire problem. I'm going to do it with the algebra. So here's our setup. We want to find theta. That's our goal. Well, we know the vector is negative rad 3, 1. And we know the magnitude we just computed was 2. And so I can set up two equations, one for the first component, one for the second. This right here would imply, for the first part, 2 cosine theta equals negative rad 3. Or in other words, cosine theta has to be negative rad 3 over 2. For the second component, 2 times the sine of theta has to be 1. Or in other words, sine of theta would have to be 1 over 2. And this is where the quadrant comes into play. You're in quadrant 2. So if I think of a reference angle, my reference angle would have to be pi over 6. It'd have to be a 30-degree reference angle to have a cosine of rad 3 over 2. But since it's negative cosine, positive sine, this would end up being 5 pi over 6 for theta. So you do need to know your unit circle. Make sure, print one out, do it every day if you need some reminders on that. It didn't specify radians or degrees. I usually will in the problems, especially when we're doing things with vectors. So you could, for this one, list it as 5 pi over 6 radians, or 150 degrees would also work. Once we start doing integration, it's going to have to be radians. Okay, last part of this section deals with forces. So a lot of different physical applications of vectors in physics and engineering. Forces, sometimes measured in pounds, sometimes measured in newtons, indicate a magnitude and a direction. We're going to look at some examples where we have two forces that are applied to the same point. These are what are called concurrent forces. And a lot of times you're going to have multiple forces acting on an object, and we're going to be interested in looking at the resultant force, kind of the combination of all of those forces acting together experienced by the object. So think of that as the vector sum of the forces. So yeah, a couple examples to take a look at here. First one, suppose two forces are applied to an eye bracket, so meaning a single point. The first force has a magnitude of 200 newtons, makes an angle of 30 degrees with the positive x-axis. The second force has a magnitude of 300 newtons and makes an angle of 70 degrees with the positive x-axis. Find the magnitude of the resultant force and the angle it makes with the positive x-axis. So I'm going to draw, here's my eye bracket here. Here's x, here's y. Okay. First force had a magnitude of 200 newtons, had an angle of 30 degrees with the positive x-axis. So this one's 200 newtons. This angle here is 30 degrees. Okay. And all of them are stemming off of the same point. So this would be an example of a concurrent force. Okay. All of them are applied to the exact same point right here. Second one had a magnitude of 300 newtons, made an angle of 70, not an additional 70, a total of 70. So the second force is going to be a little bit farther away, but it's picking up an additional 40 degrees. So the entire angle there would be 70, but 40 left over. That one had a magnitude of 300 newtons. Okay. So I'm going to call the first one force 1. I'm going to call the second one force 2. And so we're interested in the magnitude of the resultant force, meaning if I add these two forces together, so the resultant force I'm going to call just F. And that's just going to be the vector sum of F1 in red plus F2 in green. And so I'm going to write these using the sine and cosine form. So using the same angle notation we used before helps for these word problems. Force 1 in red is going to be the magnitude, 200, times the cosine of the angle between the vector and the positive x-axis. So cosine of 30, sine of 30. And so I can actually use a little bit of my knowledge of the unit circle to write that. Cosine of 30 is rad 3 over 2. So this would be 100 rad 3. Sine of 30 is 1/2. So 200 times 1/2 would be 100. So there's my first vector written in component form. Green one, vector number 2. Magnitude was 300. Cosine of 70. Remember, it's not just the 40. It's the total angle measure from the positive x-axis to that vector. Cosine of 70. Sine of 70. That one I'm going to leave because that's not on the unit circle nicely as one of my reference angles I'm used to. But now I can at least add these together. We want to know the magnitude of the resulting force. So we're first going to have to get a component form for the resultant force. Force 1 plus force 2. Adding my components together here. 100 rad 3 plus 300 cosine 70. Would be adding my x coordinates together. And then for the second one, my y coordinate from force 1 was 100, plus my y coordinate from force 2 is 300 times the sine of 70. So there's my, that's not the magnitude, that's just the force itself written in component form. And I want to find the magnitude and the angle that it makes with the positive x-axis. So to get the magnitude, same as we've been doing, Pythagorean theorem. I'm going to throw these into my calculator and see what I get. So I'm going to get 100 rad 3 plus 300 cosine 70. So 275.8. I'm going to round it on paper, leave it on my calculator. Second one is 100 plus 300 sine 70. Make sure your calculator's in degree mode for this problem. 381.9. And then I'm just going to square each component and add the results, take the square root. So square that, scroll up, grab the 275, square that, and then don't forget to take the square root. So my magnitude is roughly 471 newtons. Okay, so that tells me the size of the force. So that's the magnitude. For the direction, let's see. Where did my thing go here? If you remember, this force was the magnitude times the cosine of theta times the sine of theta. So if I want to find the actual angle now, I could either use the x or y component. I know cosine theta is going to equal, or the x component of the final force, right? Because this is going to end up being two components. I could take the x component of the final force and divide it by the magnitude. So the x component of the final force was, is that 275.8? Divided by the magnitude of the force we just found was 471 newtons. Make sure you're using the full decimals from the calculator. And then I'm going to take the inverse cosine. So inverse cosine of that ratio, 275.8, scroll up, grab it, divided by, we want the magnitude of the force, resulting force, boom. And we get an angle of about 54.2 degrees. Okay. And I could have used the sine, right? I could have done, just to show you another way of doing this, I could have done sine of theta, but then I would have had to have used the y component from the force. So I would have had to have used 381.9 over 471. So this would also be, this would also work, and it would still give you 54.2. Okay, last one I want to look at, a little bit more algebra in this one. The classic weight hanging problem, okay, from two wires. So a 100-pound weight hangs from two wires as shown below. Okay, one of them is moving to the right, hanging at an angle of 32 degrees. One of them's kind of hanging off to the left at an angle of 50 degrees below the bar. Find the tensions, the forces, T1 and T2 in both wires and the magnitudes of the tensions. Okay. So we want to actually find the forces themselves, and we want to be able to figure out the magnitudes of the tensions. First thing to notice is that you have a weight. And when they talk about weight, think gravity. A little bit of physics in this problem. This right here, this is the weight. Okay. That weight is 100 pounds. What you have to realize is that your final resulting force, when you take the vector sum of T1 and T2, it's going to have to counterbalance that weight. Just one of those properties from physics. And I'll explain what I mean by that. So in other words, if your final, your weight is pointing down, your final vector T1 plus T2 is going to have to point directly upwards. So I know this weight, if I represent this as a vector, it's pointing straight down, is going to be 0, negative 100, since it's pointing in the direction of the negative y-axis. Well, that tells me the other final resulting vector, T1 plus T2, has to point directly upwards. And so it should have component form of 0, positive 100. So T1 plus T2, it's like a little free body diagram from physics, has to counteract that gravity, that weight. Okay. Well, so now what do I need to do? Now I need to come up with an expression for T1, and I need to come up with an expression for T2. So this is where I'm going to start looking at the angles. Helps to think of this oriented on the coordinate plane. I'm going to draw this like this. Okay. Because T1 really, it looks like this is 50 degrees here, but we're in quadrant 2. So if I look at this, if this is 50 up here, these are parallel. This angle here would also be 50. If this angle up here is 32, then this angle over here also has to be 32, right? Alternate interior angles, throw back to geometry class. You get that little zigzag Z shape. These angles have to be congruent. And remember, why do I care about that angle? Because I'm trying to measure from the positive x-axis. So I need to be measuring from here. That'll help me. So I know T2 has an angle of 32. T1 is going to have an angle of 180 minus 50, because there's 180 over here. So this is going to end up being 130 for T1. So T1 is going to be magnitude T1 times the cosine of 130, sine of 130. And so that's going to, and I'll show you why I'm doing this in a little bit. Yeah, maybe I'll leave it. Let's see. Yeah, I'll just leave it as 130. So there's my first one. And just for the sake of, so I don't have to keep writing these magnitude bars, I'm going to let T1 equal the magnitude of T1 and T2 equal the magnitude of T2. So as long as you define that, you don't have to keep rewriting these. So this is going to be T1 cosine of 130, sine of 130. T2 is going to be magnitude of T2, which I'm defining to be just capital T sub 2. Angle between the positive x-axis and T2, alternate interior, that's 32. So this would be cosine 32, sine of 32. Okay. We need to find the tension in both wires, and we need to find the magnitude of those tensions. So we know, now we can add these together. I know the resulting force, T1 plus T2, counteracts that weight, and we said it's going to have component form 0, 100. but that's going to have to equal the individual components added together. So we're going to have T1 cosine of 130 plus T2 cosine of 32. And then we're going to have, for the y components, T1 sine 130 plus T2 sine of 32. And then what I'm going to do is I'm going to equate the components together. Make sure I got all my pieces here. T1, there we go. Yeah. So this first component has to equal 0. So I get really what I'm going to end up with is a system of equations that I have to solve. And once we set this up, I would encourage you to pause the video and try to do the algebra on your own, and then you can check with my result. There's equation number 1. Equation number 2, I'm going to equate the y components. T1 times the sine of 130 plus T2 times the sine of 132, or times the sine of 32 equals 100. And so, at this point, it's a trade-off. You could do substitution, you could do elimination. I'm going to probably call this equation 1 and equation 2. So I'll probably do substitution here. So if I do equation 1 would imply that T2 is equal to negative T1 cosine of 130 over cosine of 32. And then I can pick this expression up and I can substitute it in for T2 in the second equation. So then 2 would imply, with this substitution, T1 sine 130 plus, let's see. So we'll end up with minus T1 cosine 130 over cosine 32 equals 100. And we can factor out a T1 here. So we get T1 times sine 130 minus cosine 130 over cosine 32 equals 100. And so dividing out both sides by this piece, and we're going to have decimals in all these, so you don't have to do a ton of algebra to clean up the trig if you don't want to. So let's throw that in, see what we get for our magnitude of T1. So T1, which is the magnitude of T1, put it back in context from the beginning. So we're going to have, I'm going to do the denominator first. So sine 130 minus cosine 130 divided by cosine 32, 100 divided by that gives me something's off here. Okay, I found my error. I forgot about the sine 32 factor. So this part right here, let me find it. Don't forget about your sine 32. That's what I forgot. So let's go back here. This will be times sine 32. Sine 32. There we go. Forgot about this guy. And so then now you actually can make this a little bit easier. Sine 32 divided by cos 32 would be tan 32. So you don't have to do as much division. So this would end up being, let me erase this part here. Cos 130 times tan 32. We're going to divide this side by same thing. sine 130 minus cos 130 tan 32. Sorry about that. Okay. Just a lot of algebra going on, easy to miss little parts of it. Okay, let's try that again. So if we do 100 divided by, so we had 100, no, we had sine 130 minus cosine 130, nope, mess it up. Sine 130 minus cosine 130 times tan 32. And then I do 100 divided by that. There we go, 85.64 pounds. Okay, so that's the magnitude in tension 1 in the first wire. They also asked us for the magnitude of T2. We have an expression for T2. If you remember, T2 was equal to negative T1 cosine 130 over cos 32. So I'm going to rewrite that. T1. Well, now we know T1, 85.64. I'm going to use the whole decimal, though. Times cosine of 130 over the cosine of 32. So I get negative answer times cosine 130 divided by cosine of 32. Gives me a magnitude of 64.91 pounds. Okay, so now I know my two magnitudes of my tensions, 85.64 and 64.91 pounds. So now I need to go back to my expressions. They also asked me for the vectors themselves. So remember, T1 was magnitude T1, cosine 130, sine 130. And T2 was T2, cosine of, was this the 32 one? Let's see. Yeah, this was the one that was 32 degrees from the positive x-axis. So we just have to plug in for T1 here. We need to put in our 85.64. And then we're going to multiply that by cosine 130, sine 130. So T1 is represented by the vector, plug these into your calculator. I got negative 55.05 in the x direction, 65.60 in the y direction. And then for T2, I'm putting in 64.91 for T2. And then I'm going to multiply and distribute that to each component, cosine 32, sine 32. And if you do that, put it in your calculator, your x component should be positive 55.05, and your y component should be 34.40. Long problem. But we got everything they asked for. Okay? That should get you some examples to look at when you're working on your homework. If you got any questions, don't hesitate to reach out. Okay? Happy mathing.